And today the topic is variadic and variable templates. It's not that these things are very closely related, but you can have variable templates that are variadic. And since everything is very there, it nicely rhymes, so it might go together. One problem we have in C or C++, or let's say in C++, is how do we write functions that vary in the number and types of arguments. In C, you might have seen these 3 dots called ellipses for functions with a variable number of arguments. Who of you has actually implemented such a function? Oh, very experienced. The C version. Okay, yeah. So you will learn how to do it better. In Java, they stole the syntax from C and C++. You get it, but in Java, everything is an object, so the implementation is much simpler, and you got the reflection built in, so you can actually downcast safely from object to whatever you expect there. Fortunately, in C++11, we got a big relief on implementing things like this print line, really in a type-safe way. That's type-safe and easy to use, easy to implement, much easier than what you might have seen in Boost before C++11, where they provided some things that looked like variadic templates, but actually were macro-generated, huge amount of overloads. Now let's go back to those of you who have used var args to implement something like a print with a variable number of arguments. You have to use magic like VA list, VA start, VA end. Who has never seen that? Lucky. And all the others, oh. And to actually access each element, you have to specify its type, and you better know that in advance, otherwise you're host. And if you, let's say, pass in something else than an int, bad luck. Because it will be cast to an int or interpreted as an int, and you might not even know what it was. Yeah, that's it. So that's not what we want to implement. It's there in the language because printf needs it, or scanf. It's never checked by the compiler. Some compilers get clever with printf and scanf and know what the percent format string is supposed to be, but that's a string, so you can compose it yourself, and your actual arguments might not fit to what you actually expect. Especially in the case of scanf, it can be quite have interesting effects. And so we need, if we want to use var args or the ... ellipses in C++, classic C++, we need to know the type of the additional arguments, the ... arguments. We need to know the number, and all that is implicitly, or we have to have a fixed, because I cheated, I had this fixed list of ints that I was expecting on the example on the previous slide. Now in C++11, or just a reminder, in C++ we have functions that can be overloaded. There's the magic of overload resolution through the call argument types. Remember? Yeah? It's like a puzzle where you fit in the correct pieces where it should go, and if it's fit, the compiler selects it. The bad thing about that, you might get overload resolution with ambiguities. Who has never had an ambiguity in overload resolution? Okay, that was the expected reaction. We have function templates who provides us with almost unbounded overloads of a function, where we have the template argument deduction, and that's one of the magics in C++ that actually makes it so fun to write function templates and to work with function templates, because you don't have to spell out the angle brackets and the template arguments, but still get the template. In class templates, we don't have overload resolution, but we have also some magic there, the selection of a specific implementation if we have template specializations. Who of you has done a template specialization so far? Wow, you're all experts. I am teaching that to you. And there's a thing called pattern matching. I would say it's a compile time if. So whenever some functional programmer tells you about pattern matching, well, it's if or set or switch. How do we define a variadic template function? So a little bit of new syntax around these 3 dots. It's a template, and to introduce a list of types, we write type name ... And we can get that, give that list of types a name, and in classical template manner, I actually used args for that. And whenever I present that slides, I hate it because it's args and args. So capital args are the list of types. And then we just specify the function. It has a name, a return type, and if we want to have these capital args auto-deduced, we better use them as function arguments. So we use that args, capital args, ... meaning, please, dear compiler, take all the list of template arguments, type name arguments, and define a function argument for each of these types. And to give these function arguments a name, I use the lowercase args. And I hate myself again. I forgot to change that. And, well, I'm not showing you what to do actually with these args, except for whenever you spell out the name with the ... on the right-hand side is a so-called pack expansion. So you take the list of either parameters or the list of types and expand it, create the list. If you put the ... on the left-hand side of the name is when you define actually the list of things that is variadic, or where you have many. So the nice word variadic only means you have many of something. And there's one specific extra piece if you use size of ... which is a special version of the size of operator. It will give you at compile time the number of elements in that so-called parameter pack, which could either be the list of types, capital args, or the list of function parameters, lowercase args. And in this case, both will be the same size. Any questions? Now, this is not very interesting because it just delegates whatever Variadic is supposed to do to that print line, that magic print line that I promised to you. Now, let's have a look. How do we actually implement and use these Variadic functions? The key thing is recursion. And whenever you have recursion, you have to have a base case. So I provide a base case overload, a print line with no additional parameters except the O stream we want to print on, and that does just printing a new line, which is OK. Now, to actually implement the rest, well, it's a typical thing. We chop off the head and take the rest of the snake or whatever, the number of arguments to implement that. So this print line actually takes a regular template parameter and then a list of things that I call tail here. And by matching, it takes, OK, at least one head element, which is output. And if there are more elements available, it outputs a comma and then recurses on itself with the remaining elements. And because that is a template, it's a compile time thing. And let me show you some code. I hope it's readable. So this is our print line. And this is a feature I show you because that's not yet available in Develop, but it's implemented as you see. It shows us the template instantiation. OK, this print line call is actually taking a character array with 4 elements, an int and a double. And if you look closely, 1, 2, 3 is exactly like that. And if I drill down, I can look into the, let's make that bigger, can look into the implementation where I say, OK, I have the head is the character with 4, and then the tail and it goes down and calls print line with int and double. And then we have only the remaining double. And now we see we have a, I'm not sure, the tail is empty. Let's see if that's magic now. If it works, it works. Ah, I get to the base case of my recursion. So I can actually drill down through the template instantiations to see what's going on there. Cool, isn't it? So now I hope you understood the magic behind. It's not really magic, it's just providing compile time recursion and see what happens. There are a few of the interesting parts when you do that. The first thing, the recursion needs a base case even if it's never called. I just changed the code a little bit, so I only recurse if there is more to do, and do the new line, let's say, within the print line function itself. The problem is, while it would never call a print line with an empty tail, the compiler would still need to compile that piece of code. There's a question. Wait for the microphone, or say it and I will repeat it. Or wait, the microphone is running up.
Can a base case can just have single argument? Will see out any single argument and never call anything else?
The problem is, well, I could have a base case with a single argument. That would work.
And stop the recursion there.
What's that?
And stop the recursion at this moment.
I could stop there, yes. But here, but then I would have code duplication of this, let's say, separation and the output of the head. So it's, you could end with the base case with a single argument or with zero, but you have to have a base case. With just this function definition, it won't work. It won't compile, actually. There's another interesting part. If I change the sequence of function definitions, let's say put the Variadic template version and the base case in the opposite order, it also won't work. Because that's one of the dark corners of template instantiations. The name lookup done here will only see what's defined up to this point in the source code and will not see this definition if it only defined or declared later. So you better declare your base case before you define the Variadic function, otherwise it will not compile. And there, if you Google Oliver Maudal's pub quiz, there's an interesting part with templates where the lookup just fails. And that's, or if you have multiple cases you want to select or multiple overloads, not only two, then it becomes interesting. And there's another question.
Well, actually, sometimes you can place this function under this template if the call to this function uses argument-dependent lookup.
Yes, I was lying a little bit, yes.
Yeah, so in this case, it doesn't work because your function is not in the namespace std and
exactly.
ostream is, and if you were using not std ostream but your own class, then you could actually put it lower.
But most of the time, the base case will just have no arguments, and then it won't work. So that's a better rule of thumb. You can make it work with namespaces and your own types, but even then it's magic, and ADL is magic as well. If you get problems with ADL, it's hard to understand if you're not very familiar with that. So better rule of thumb, declare everything up front before you implement it. There's another question here.
Wouldn't it work without a second recursion function if you can express it in a constexpr function? Because constexpr function have this property that branches that are not used are not compiled.
Only if you not use it in a runtime context.
Okay, yeah.
So a constexpr function at a constexpr time might be able to, but even then the compiler will need to see it. And so it's, I could try that in the break if you want me to. But with OStream, I have no chance of using it, doing it. I want the side effect, and that's my example here. And we get more on constexprs later. Now, we can also have, let's step aside from variadic function templates at the moment, we can also have variadic class templates. And I'm still looking for variadic class templates with type name template parameters that are something else than tuple. The most important usage is actually tuple-like things like tuple or similar things. And it's, for me, it's very hard to imagine use cases for class templates with type name parameter packs that are not tuples or are not for metaprogramming. If you have a good example, please tell me, send me an email, because that's, I always look for good examples to motivate that, because not everybody is actually implementing tuple. It's actually, to do it well requires a lot of jumping through hoops to make it compile fast and stuff like that. Okay, we can have empty tuples. That's the easy part. Or we can make tuples. And there are two ways of making tuples. One is called make tuple, and the other one is called tie. And the difference between make tuple and tie, make tuple creates a tuple of values, and tie creates a tuple of references. And that's a nice trick, because you can actually have multi-assignments now, where you write tie equals a tuple, so you can actually have multi-assignment in a single line of different types with tie ABC or ABS equals make tuple 1, 2, 3, and that would be would just work. Who is seeing the trick that I'm using that it actually compiles? Who is C++ forwarding?
Yes, behind 3.
Oh, the answer is I used the literal suffixes standardized with C++14, the little s in the namespace, standard string literals that makes a string literal a string object. Because then my tuple of a tuple, the type is a tuple of int, double, and string. And that actually matches the types of A, B, and S that I use with the tie assignment. Tuples can easily be overused. This is from code that I reviewed from, let's say, real-world code base. It's got changed in between, but that's a misuse of tuple. Just because someone needs to return 3 bools, meaning something, doesn't mean it's a good idea to use a tuple with 3 bools to do so. Don't do that. It's pink, and pink is, or it's reddish things or red things. Don't do that at home. Especially because you have now indexed things with 0, 1, and 2 without any clue what those means. Only by the positioning in the tuple and in the argument list, they have a meaning. That's a very bad idea. It's no problem to provide your own abstractions. If you have combined values, you can just do a struct of 3 bools, or even an enum type where you have bit flags in the enum values. That's fine. Don't use tuple unless you're writing generic code. And the standard library is guilty. The standard library uses pair as a return value for different purposes, either in maps where you have the key value as first and second, but some algorithms return an iterator and a bool, or a pair of iterators, and that's not what you want to use pair for. Why not say iterator pair as a type instead of pair of whatever? What are another use of, so we got functions with a variable number of arguments and types. we got tuple-like things, but there's another use of variadic class templates, and that's template parameters. Who of you has written a template class using template parameters? Who have never heard of template parameters? Okay. So, who has never heard of template parameters? Go home, take your C++ lesson. Maybe read Van der Waerde book on templates. And the other use is non-type template parameter. Who of you has written a template with non-type template parameters? Who have never written a template with non-type template parameters? Okay, you all are template meta programmers. Cool. And the interesting part that came with C++ 11 and 14 is integer sequence and computation of value sequences. And we will see some examples in some minutes. Yeah, we have time. Just to give you a context of the template parameter. This is one example I do in my lecture. It's actually suits the day tomorrow. We have Santa Claus, and it comes with a big sack or bag of presents. And the idea of a sack is you put things in and get them out, but in some random order. Actually, yeah, and I'm cheating. That rand is not rand. It's using in real world no longer. This is deprecated, the classical C rand. But you can spell it the same with the magic in C++ 11 features. So, but a vector might not be the optimal data structure for actually taking something out of the middle and giving it away and throwing it away from the data structure. So we might want to have, if we have a very big sack, vector might be not the optimal one, or you might pretend it's not the optimal one. So how can we vary our sack template class to vary actually in vector? The first attempt, yeah, that's what I said. The first thing is our API. We need to use in our vector class a little bit more generic version of, we cannot rely on the random access iterator and so on, but it's not really an issue. And the first attempt would be, okay, we pass in the container that we use as a template parameter. And since we have our present type T, we take the container with the single type name argument. The problem is, will that compile with std vector? It says doesn't work, but why? Well, vector has actually two template parameters. The one is the element type, and the other one the allocator type that you usually don't care except you are on an embedded in the embedded world or in very specific resource environments. But still, vector requires two type name template parameters, and that wouldn't fit with this template parameter declaration. Now, and that's now where actually variadic template come to the rescue. Wow, what are we doing? We use a template parameter that is a variadic template with any number of type name arguments. And now std vector suits well, but we could use std list or even std set, which has 3 template parameters. It just works. Unless you do something where the concepts of the underlying container are violated. But this way we can actually vary the container and make really use of these 3 little dots. Anybody done that already? Why are you here? Okay. This is just the scaffolding, how to do that with if you have a factory function where you would deduce the element type from an initializer list, you have to switch the arguments because then you want to specify which container to actually use. And since argument deduction always works from right to left in the template parameter list. We have to switch these things to have the container that we specify after make other suck deliberately. So we can actually do make other suck std set and provide something. And that's kind of reddish because we provide a list that actually doesn't go all into this, the suck because the C is there twice. Questions? Okay. Variable templates. Actually, the big thing about variable templates, they're not variables, but constants. Okay. But why are they called variable templates? Well, because all constants or named constants in C++ are actually syntactically variables. They have a type, a name, and a value, but just they are const. And the variable templates are constexpr. Why would we want actually to have these things compile time computation? We can get rommable data. So for the embedded world, this is a feature that might be really helpful to get guaranteed data into ROM by computing it, pre-computing it at compile time. And I think time will permit us that I show you the example. It's plain C++. The syntax, actually the feature of having something like a variable template was available since C++ 03 or 98. It's just too ugly to use and a little bit complicated to use, but it's not that variable templates are something you couldn't simulate in C++ 03. And not everything you could think of is provided. There are some, for example, the constexpr compile time computations. There are deficits in the library, like std array, for example, is not as constexpr as it could be, so you cannot use a std array as a plug-in replacement for plain arrays in constexpr functions. But I don't want to go too much into those details. But I want to remind you, compile times can increase horrendously with interesting compile time computations in C++ 14, or even in C++ 11. But C++ 14 makes it easier to increase the compile times, and I'll show you an example towards the end. Just a reminder, some terminology. We can have compile time evaluation, and there's something called a constant expression context, like the array dimension, the array extent, when you define an array. In C++, this has to be compile time computable, and our sz variable is actually a compile time computed, so I can create an array of its size, a number of elements. The problem is I cannot do much complicated things except with macros that are actually then expanded by the preprocessor to do more complication. And except for the constant expression context, I have no guarantee that my size sz variable is actually computed at compile time. It will be in that simple case by, I would say, any compiler, but it's not guaranteed. Only when it's used in the constant expression context, I have the guarantee that something is computed at compile time in C++ 03. Now, let me show you how to do variable templates in old C++. The underlying idea is I have a template class with a static const member, and I can actually compute factorial based on an integer value at compile time. Again, it's done through recursion, and the recursion, again, needs a base case for compilation. Even though this base case might not be used in the computation, it still needs to be instantiated and stop the recursion of template instantiation. So you cannot omit this base case full specialization of our factorial template class. And the proof in the pudding is using it in a constexpr context. So we can, if that compiles, we have the check that the factorial 5 value is actually computed at compile time. Otherwise, the array wouldn't be able to create it by the compiler. The bad thing, we can only use more or less integer values as template, as non-type template argument parameters and arguments. So that's a problem here. And well, this is C++03, therefore I didn't check it. The value I just check indirectly the size of if that's correctly computed. So it should be something like whatever factorial of 5 is. Anybody done this? All template metaprogrammers, cool. Now in C++11, we get this new concept of constexpr functions. That wasn't in my title, but I better explain that. So I can implement factorial recursively again, but now as a function. C++11 has a restriction of a single return statement in constexpr functions, which is quite limiting, but still general enough to be Turing complete. So you can, in principle, compute everything. It's just too ugly to spell it out. Again, the check is there if the factorial can be used, and that's also compiling. We have the constant expression log variable. The C++11 compile time, constexpr function limitations are really a limitation and sometimes a pain in the ass if you want to use it actually, and that's where C++14 is a big relief. But it's also a very, very big burden for the compiler implementers to get constexpr computation in the compiler right. Because you have an almost complete, to implement an almost complete C++ interpreter within the compiler. And we are trying hard to make that in our cvelop or Eclipse CDT parser to be able to compute C++14 constexpr. And one of my students is sweating hard just right now to get that done. Or maybe not on Saturday, maybe on Saturday, yes. He's sweating. Now, let's look back. Compile time in C++03, ugly syntax within a struct, a template, and so on. And it's actually, the struct is not really, the struct and the static stuff is not really that interesting. So what we can actually do is, let's see if I can make it work. Ta-da. Just make it simpler. So we can actually compute factorial with the variable template. So it's a template here with a non-type template parameter, a number n. We say the variable fact is computed by taking n times fact n minus 1. And we provide a base case for the case when we have 0 as the n, because then the factorial is 1. So whatever we did as a constexpr function, more or less in C++11 syntax and C++14 with the variable templates, we can compute at compile time the factorial, unless we get a numeric overflow. Then that might be a problem. With size, it's not a problem, we just get funny numbers. If it would be int, it's a bit of a problem because that would mean that we, whenever we get into the case of undefined behavior at compile time, that means it's a compile error. Lucky for us. This is the example you find in the standard. That's one of the most brain-dead things to do, but it's possible to define constants based on the type, like pi, based on t. So you can make t a complex double or a float, or even make a pint out of pi int, which is 3 liters or whatever your measure is. These variable templates, again, are always constant, compile time constants, and they will be computed. That's the generic example. And whenever you do compile time computation in C++14, auto constexpr should be on your let's say, auto expansion key on your IDE. C++14 constexpr functions are much more relaxed. You can have local variables of literal type, which were local variables were verboten in C++11. We have loops, we have recursion as always, we have arrays, we can have references. We can have even branches that rely on runtime features if they are never taken at compile time. And some people use that to prohibit use calling such a constexpr function at compile time, because constexpr functions, because of the limitations, might have a bad runtime behavior. For example, if you would, let's say, make the copy algorithm of the standard library constexpr, it would always require, let's say, copying element by element, and you cannot optimize it for, let's say, if you have a random access iterator with a contiguous memory block to use memcopy, for example, which is doable in some implementation of the standard library. And you can use almost all C++ statements in a constexpr function in C++14 that doesn't use any runtime features like memory allocation. So new and delete for the heap, there is no heap at compile time. Exceptions, there are no exceptions at compile time. Whenever you use such a feature in one of the branches taken at compile time, it will be a compile error. Now in C++14, we can have a simpler implementation of factorial and just multiply in a loop. We can have side effects and local variables, and a parameter is also a local variable, and it still works, and we can have return type deduction even with multiple statements in there. And we have static assert, where we can actually assert that our, remember, variable template version computes the same value as our factorial constexpr function. The interesting part is, here we have loops that are computed at compile time. What if we have a deeply nested looping things? That might end up that you either hit a compiler limit, which is typically around the default around 1 million, let's say, iterations or statements taken. It's similar to the limits you might get with template instantiation depth, but it's much easier to reach because you're much easier to inclined to write a loop just at compile, and that's computed at compiler, than to write deeply nested template instantiations. And the calculation is done in the context of the compiler and not the target platform. That might be interesting for those people who might have different, let's say, double number representations, floating point number representations, or different limitations like on numerical values allowed. So, if you overdo it, we get back to that XKCD comic, it's compiling. So we can all do sort files. Now we have all, again, laser sorts because of Star Wars coming out again. So you can have a laser sort file in the office when compiling. It's a kind of, we had that in the 90s with the C-front-based compilers where template instantiation was really slow and the then current machines. And now we can easily get there again with constexpr compile time. So don't overdo it. Return type deduction, I already told that. I will want to show you more example code. Who knows FizzBuzz? Who has never heard of FizzBuzz? Okay, who wants to explain FizzBuzz? Okay, there's one with the microphone.
No.
Yeah, now it's your turn. Go ahead. You don't want to explain FizzBuzz? He's a volunteer.
Okay, as far as I know, FizzBuzz is task given during interview rounds, and the question is print numbers from 0 to something to 100, where every multiple of 3 is replaced with fizz, every multiple of 5 is replaced with buzz, and every multiple of 15 is replaced with fizz buzz. Is it correct?
That's, well, actually, it's a children's game to learn about division and multiplication of 3 and 5, but nevertheless, it's often used now. Maybe Kevlin is guilty as an interview question in when hiring programmers. Actually, it's not that much interesting as an interview question, but again, I show you another version of FizzBuzz because Kevlin Henny has several dozens of them in all kind of languages, and I'll show you the one, or I could even show you 3 different versions, but I will more or less show you one in FizzBuzz. So the idea is we want to do it at compile time as a constexpr function, and we want to do it interestingly by passing in the list of values, let's say 0 to, I think my biggest version in the test case is 16 because it's just too long to spell out by hand all the expected outputs, to pass it in as a template parameter. A template parameter, values. And it uses a feature of the standard library called index sequence. Actually, index sequence is a tricky thing. It takes a list of unsigned integral values and turns that list of values into a type. And each different list of values is a different type. And who can guess what the size of such an object would be? There's someone smiling. It depends, but it's very small. It can be 0 if it's used as a base class, and it might be some limit your compiler puts on an empty class, because the type itself doesn't have any data members. The data is all encoded in the type. And how do we implement it? Again, we provide a base case overload for an empty index sequence, and I've selected to use tuples. You see why I explained tuple to you. An empty tuple if the index sequence is empty. If I have a list of values in the index sequence, I cut off the first value and take the remainders. And I combine using tuple cat. The tuple I get from this special case single value index sequence. I could have used integral value here. Function call with the list of output of the rest. So again, recursion, chop off the head, like in the French Revolution, and then do something with the body. Now, what is integral index sequence? We have this in the standard class type called integer sequence, and it takes a class and a list of values of this class type, and the class type, because we have a list of values, must be integral type, otherwise we couldn't give a list of values. And for a size t, we have the template alias index sequence, where we have a size t with a list of values. The interesting part, when I call, let's say, here, 1 is a template argument, and it gets automatically deduced when calling out to FizzBuzz number. And make index sequence actually creates an index sequence with a list of values 0 up to n-1 as a type. So everything is done at compile time without any runtime overhead. Still here? Okay. Now, how do we implement all that? Okay, for a simple number, we have a base case where we just say make tuple of that number. But that's wrong for the cases of 3, 5, and 15, and all the multiples. So we can say, okay, for 0, we make the empty tuple because 0 doesn't output anything. if we have this 3, it will output fizz as a tuple. If 5, it will be buzz, and if it's 15, it will be fizz buzz. The problem is this doesn't scale because we forgot 6, 9, 10, and 12. And if we would have to list all of these, we would be a very bad programmer because it would spell out all the cases. And I'm sure Kevin Henny has one example where he just spells out all the cases, and this is the program. So that would be the enterprise version, spelling out all the individual cases. We have a lot of code not doing very much. But we can test that already, so we have some test cases. So if we change the implementation, make it better, we can at least guarantee that our version of this fizz-buzz number thing is working. Now, to get that is we use enable if. And the standard library provides that. And who has used enable if? Who has never used enable if? Who has never heard that there exists something like that? Okay, what is enable if? Enable if is a means to make compilation fail, but fail in a way that it's not a compile error. What does that mean? It makes sense in the case where you have templated function overloads or class template specializations, where you might have ambiguities or multiple versions that fit, and the compiler will always select the one that fits best, if there is a single best. If there are multiple bests, you get a compiler error because of ambiguities, but if there are single best fit, this one will select. And if there are multiple slightly good fits, enable if can help you to select a specific one. And it does usually do that by either providing enable if with the as an additional template parameter, or as an additional function parameter with a default value, so you will never specify it when you call that function. And what we are doing now is, okay, enable if takes a compile time expression as actually, yeah, as a template argument and the type. And if its compile time expression evaluates to false, it will create a compilation error. But because our fizz-buzz number is a template function, we have a thing called sphenae. Who knows what sphenae stands for? Who has never heard sphenae? Oh, only very few. Sphenae stands for substitution failure is not an error. So if we, and the point is, if we attempt to instantiate a function or a class template, and that fails because by instantiating the template, a parameter is not valid, compilable, then it's a silent error, and the compiler just attempts to instantiate the next function. And this is if value modulo 3 is 0 and value modulo 5 is 0, then the first enable if fails to compile, and the compiler says, okay, skip that version of the template fizz-buzz number, I just go ahead and look for another one. But if it's not divisible by 3 and not divisible by 5, we just take the numeric value, and create that as a tuple. Now, if it's divisible by 3 and not divisible by 5, we create a tuple with the character array fizz. And now you see why I use tuple as a value and not anything else, because a tuple I can combine later on numbers with strings. And you might see the pattern. If value is divided by 3, not divisible by 3, so we get a remainder, but dividable by 5, we get a buzz. And if it's divided by 15, we get a fizz buzz. So we have 4 cases: the number, fizz, buzz, and fizz buzz. And just to show off, C++11 had enable if, where you have to specify : type and type name. And C++14 with template aliases provides _t as actually an alias for this type name thing. So it's much shorter to spell out. Testing it. So I create a tuple with the values that I expect: 1, 2, fizz, 4, bus, fizz, 7, 8, fizz, bus, 11, fizz, 13, 14, fizz, bus, 16. And I stopped there because I didn't want to go up to 100. And well, there's some conditional compilation because I had a simple but wrong version and another problem there. But we want to actually do that at compile time, so you better check at compile time that it works. And fortunately, we can compare tuples if we can compare the elements. And we create the tuple again as a constexpr variable. We take a result by calling out the constexpr version of fizzbus and expect that it's a compile error. And I show you it's a compile error when violated. So let's go to the IDE again and see if we can show that to you. I have to get... Now here you see a lot of scaffolding. That's the fizzbus number code. That's the actual recursion code. And again, you see first the template declaration, base case implementation, actual template implementation. And we skip over that and look for the static assert. This one. And now I produce a compile error by saying, okay, I want 17 here, just to make sure we get a compile error. And I just need to find the console. And we actually get a compile error. Static assertion failed. Fizzbus should work at compile time. Now fix it again. 16. Okay, everything is fine. Static assert is true, it worked. We can also create from the constexpr function version a version where we can just specify the n. So we get to our case with the 100 if we want to. And we just say, okay, we make a template variable, fizzbus v, taking n as a template argument. And we create it by calling fizzbus with make index sequence of n elements. So we get a list of 0 to n minus 1 and create the fizzbus tuple and put it into fizzbus v. And again, we can have the same test case, make the tuple with the values, and say we expect that fizzbus v of 17 is exactly that content. And I can show you again the variable case. That's the static assert of the variable case. And we use the same expected, so we have seen actually the same, just make a different compile error by stopping short here. And now the compile error gets a little bit more interesting. And a bit more interesting, and a bit more interesting, and now it's done, and it's all... You see a lot about tuples implementation in the back because of the recursive version of the tuple, and the static assertion failed. Tuple objects can only be compared if they have the equal size. At least the compiler has a quite decent error message in the beginning. So let's fix that again. It was 17. Should look good now. Yeah, that's fine. Okay, just for the fun of it, we implement another variadic template, and now I'm cheating again with putting something in the namespace standard, and now our friend with the ADL example, and I forgot who that was, somewhere in the back there. That's to get ADL with the shift operator here, because I want to print a tuple, and I don't have an overloaded operator for shift operator for tuple in the standard namespace, but I put it there to cheat to be able to actually use it. And my T's are also not in any specific namespace, so that's why I use it there. And to implement that, I rely on my print line function that takes any number of arguments. And now I need to map the tuple values of the specific type to function arguments. And fortunately, that got standardized as well, or will be standardized as well. We have this apply function, or will get apply function in the standard, is in the library fundamentals TS1, if I remember correctly. Actually, I wrote the spec for it because I just took the example Jonathan Wakely put in for index sequence in the standard of C++14 and said, okay, why don't we provide that apply function as an implementation in the standard as well? And that's how it got there. So actually what we need to call is our printer lambda with get 0, the first element to print, get 1, the second element to print, and all that. And that's what apply is doing. One thing to learn as well in C++14, we have variadic lambdas, and in principle it should use sit forward here, but I didn't do that. So we can have lambdas with a variable number of arguments, but you cannot write recursive lambdas in C++. So to actually implement those, you always have to delegate to a variadic template function or a variadic function. Otherwise, you would not be able to actually recurse correctly. Now, how does apply look like? It actually shows you a little bit of interesting pieces of pack expansion. The pack expansion not only works for a single name, but also for a whole expression. And it will generate a list of these expressions for each of the elements of, for each T you get there, you will get here whatever you, actually not for each T, but for each I. That's it, the index sequence here. You forward to the function f, which is our lambda, get I, which is an index out of the list of index values, and forward the tuple to the get function to actually get the value at the position I in the tuple, and that for all i's passed in as the index sequence, and because we don't want to spell out 0 ... to up to the number, we do that with the make index sequence out of the tuple size and pass this type, which is actually an empty value, just a type with the right number of indices 0 up to n into up to n minus 1 into the apply impl function. And whoever understands that on a first impression, I'm impressed. So that's actually something you will never need to write again in the future, because it's as an example in the C++14 standard, and it will be in the library in C++17. Now, let's see if we can actually output these things. Oh, no, I'll leave that as an exercise for you. You can download the source code. Let's do something else. Now, who is doing embedded programming for controllers or whatever in C++? This is, I show you how to do it, but also how not to do it. Assign table. So sometimes it's interesting to have a table of lookup values for interesting functions that are expensive to compute at runtime. Anybody done that? Okay. This is how to do it in C++. In the past, many people wrote, let's say, a Python or a Perl script to generate header files with the tables. There's some nodding, yeah. No longer. You can do that in C++ as well. So what I want to show you is actually a variable template make sinus table where you pass in the number of steps you want to take around the circle and a double value, and these are the test cases for that. How is that done? You construct the table with the function, a constexpr function, template function, passing in the type as a template parameter, so we can get whatever value type you have. We use an array, initializing it with the sign of the indices adjusted with the 2pi, which is also a variable template, which is actually pi times 2. And the implementation of that sign cannot be the standard sign function because that's not constexpr, so I implemented my own, which is very, very bad because of my lack of math. It's a Taylor series development, and that converts badly, so I first adjust my value, which I expect to be some doublish thing. I should have made that as well, templated around 0 in the interval minus 2pi plus 2pi. And that's pi and 2pi. We've seen that. And another nice thing that you can do without any problems is providing a constexpr, a variable template for where you can specify degrees. And oh, that's the slide. I didn't adjust the slide. In the code, it's Berlin North and Berlin East. And that's how you get variadic template. And I want to show you something for sword fighting, and you can actually do that and ask questions in the time. So we have our Taylor series source code. That's the implementation that we've seen, and that's the test case. And just to show you that it compiles, I should compile, and it compiled previously. And if I just make it, let's say, 4 times 360, so every quarter of a degree, let's see what the compile time will be. It might get a compile error because we reached the limits of the compiler. Well, actually, it worked. Let's do it 10 times. It doesn't work for every minute. Now we have the compile time. So questions? And we get an interesting compile error. Now we can cheat again because what it actually says, constexpr variable must be initialized a constant expression. But actually what happened, constexpr evaluation hit maximum step limit, possible infinite loop. So the compiler protects itself, and I might be able to cheat a little bit to tweak that. Let's see if I have constexpr. Oh, I already put in a big number there. I'm not sure if I can add another 0. Let's try that. Okay, questions? Doesn't help a lot, so problem. You see, it's either compiling or not compiling. Questions? Otherwise? Yeah, okay. Microphone? Or speak here.
Okay. It's not completely related to this, but sometimes I need to do a check, a compile time check that I want to do when the function is evaluated in the constexpr environment, and not to do that, or do a runtime check if I am in a runtime environment for that constexpr for that function evaluation. So Is this possible?
I know it's possible, but I don't know by heart. But there was a talk at CPPCon by some other guy whose name I forgot, who was explaining about constexpr function and exactly showing the trick to be able to either determine if a constexpr function is called at runtime and prohibit that. I think the trick is throw an identifier where you declare it but never define it, then you get a linker error. And the other trick is to actually throw at compile time if it's called at compile time with an invalid argument.
Thank you.
So it's doable, but I wouldn't be able to write it down right now. Any more questions? Okay, now you all go home and try to implement everything with constexpr and variable templates and constexpr function at compile time, so we can actually have these laser sword fights in the office. More questions? Don't hesitate to contact me via email. Try our free IDE for C++. If you try it and it fails your expectations, please tell us, because we want to learn how to improve it. And because it's free, it's easy to just throw it away, but we really rely on people's feedback to make it work better, because my goal is to make it the best IDE for C++. I now have a big competitor with the JetBrains guys who are doing a good job there as well. But we try hard to make it, especially for make refactorings work for code modernization. And I told some of you might have been in the other talk, like doing things like template parameter extraction from non-templated code to make that easier. And I have a student working on const cleaning suggestions, so where you can add const to that. But that's not available yet for the general public, but maybe next year. Hopefully next year. Thank you very much.